Let's talk about sampling distributions. Hi guys, welcome back. This is going to be the first of 3 videos on sampling distributions. In this video, the first video, we're going to talk about the sampling distribution of sample means. In the next video, we're going to talk about the sampling distribution of sample proportions. Finally, in the third video, we're going to do some practice problems. Okay, so we're going to talk about the distribution of sample means. I want to make sure right at the beginning that you have a really clear idea of what a sampling distribution really is, because it's kind of abstract, and a lot of students have trouble with it because of the abstractness, and also because as you're looking at the sampling distribution, there's this nagging feeling in students that maybe they don't understand it fully because it's not clear what it does or why people would use a sampling distribution. You may have that feeling in just a few minutes. If you do, it's okay. At this point, I'm just going to put it out there and say it straight out that a few of the things that I talk about in this series of 3 videos, you're going to have to sort of take on faith that it has a purpose, it has an important purpose, and it's a valuable tool. But right now, we're just learning about how the tool works. So you're going to have to leave the understanding of the utility of it for later. Just because you don't see the point doesn't mean that you don't understand it. So I've drawn a normal distribution here, as close as I can get it with my level of coordination. And I want to talk to you about what a normal distribution is composed of. Think about what that means. We have a number line on the bottom. That's the real line. That's the x-axis on the bottom. And if we have a distribution, a data distribution, a population, or whatever it is that's normally distributed, it's normally distributed because we have a lot of scores that sort of almost literally pile up around the mean. It's very normal to be normal. So you have a lot of scores there. And then you have a few scores that are very high and a few scores that are very low. And the further away you get from the mean, the further you get, the fewer are the scores that exist there, and that's why it tapers this way. The important thing to note here is that this curve is made of scores, and they are piling up in the center and they diminish towards the edges, so that's what it's made of. So in imagining the sampling distribution, we're imagining taking every possible sample of some given size from the population. Let's go back to our population with a mean of 20 and a standard deviation of 2. And we're going to go through and take whatever that enormous number of samples is. We're going to take every last one, and we're going to get a bunch of different means. This may not match the first list. It won't matter because we're going to imagine thousands or millions of them, and they're going to take on just about every reasonable value that you can imagine. This list would be thousands long. Keep that in your mind. What we're going to do is we're going to graph those. And here's where I'm going to contrast the sampling distribution with a normal, regular normal distribution. Instead of being a distribution where the distribution is formed by different scores, we're going to take all those sample means that we just started to list. I had 4 of them there, and we're going to graph those values. They're just numbers. We're going to graph those values on a curve. So instead of being formed of individual scores like the first normal distribution was, this distribution is going to be formed by the means of all the many samples that we take, whatever they are. There's going to be scores of them. A lot of them are going to be close to the center because that's close to the mean, and we're going to get many samples where the mean of the sample is similar to the mean of the population. We're going to get a few samples where their mean is very different. This will be X bar number 950, just to pick a number randomly out of my hat. So that mean happened to be a very large number. Here's x bar number 951. For some reason, the next one we took, as we took these many samples, was very low. If we take all those means of all those samples and we graph them under the right circumstances that I'm going to go through, we're going to get a normal distribution. And this is a very, very powerful and useful tool. You just got to sort of hold on a little while before you see the real utility of this. For now, it's just important to get the concept. So we now have two objects, or if you want to think about it, we can actually expand our definition. But for right now, we'll think of this as being the second of two objects that we have that look very like each other. The first one was the normal distribution that represents a normally distributed population. It has a mean. We said it was 20. It has a standard deviation. We said that that was 2. And that's what we're familiar with. Now we have the sampling distribution, which looks the same, but it's composed of the means of all the many samples that we might have taken from this population. So each of these you might think of being as samples. We took those samples, we measured their means, we took those numbers, and we graphed them. And here's the sampling distribution. So we're going to start getting used to some of the nomenclature and some of the symbols that we use in talking about the sampling distribution. This is actually mathematically a different object from that. That's the distribution of sample means. So it has a mean itself. It's the mean of all the means. Don't get confused by the circular nature of this. The mean of the distribution of sample means is actually literally called mu sub x bar. And that makes a lot of sense if you think about it. It's the mean of all the sample means. It has a standard deviation. After all, it's just composed of numbers. They happen to have come from the means of all the many samples, but once we graph them, they're just numbers, and being a distribution in itself, it has a standard deviation. That standard deviation is called sigma sub x bar. And in the next part of this video, I'm going to talk about how you figure out what those various values are, because we need to start talking about this new distribution, the distribution of sample means, and how it relates to the parent population that it came from. Okay, new object. We're going to talk about that next. In fact, in talking about it, I'm going to list 4 rules that you really need to learn as the heart of your understanding of sampling distributions. So here's these 4 rules, and they're going to answer what I just proposed that we would be talking about, which is how do you determine what mu sub x bar is and what sigma sub x bar is. Well, the first rule is mu sub x bar is equal to mu. What does this mean? This means that the mean of our sampling distribution is equal to the mean of the population that it came from. If you think about this a little bit, it seems too simple to be important. It's very important. And it seems kind of arbitrary, but it's not. If you think about it, the mean of the sampling distribution must be the same as the parent population. After all, we're really talking about all the same individuals contributing to the curve. In the case of the regular population curve, each individual goes onto the curve and contributes once to the size and shape of that distribution. They contribute equally, just once. With the sampling distribution, all of the individuals in the population still contribute equally to that distribution. They're just doing it via all of the many samples that they are members of. So the mean of the sampling distribution is always equal to the mean of the population. Remember, we're assuming that you took every possible sample possible from that population. Here's the second important rule. Sigma sub x bar, and by the way, that object, that thingy, is so important that we give it a special name. It's going to be called the standard error. But you can always call it sigma sub x bar, or you can call it the standard deviation of the sampling distribution. You can call it those things, and you'll never be wrong in doing so, but it's also called the standard error. It has its own name because it's so important. The standard error is actually sigma divided by the square root of n. Let's point out a couple things. That's sigma, meaning that's the standard deviation of the parent population. That is lowercase n, so that is your sample size. If you'll remember, I was proposing in an earlier part of this video just a few moments ago that our sample size would be 2. Well, to make this easy, let's use a sample size of 4. Our parent population, the one I started out by talking about, had a sigma of 2. Let's imagine that we have a sample size of 4 that we're now working with. Well, that would make, in that case, the standard error would be 2 sigma divided by the square root of our sample size. That's a pretty easy calculation. That would mean that our standard error in that case would be 1. So the sampling distribution that resulted from that, from a sample size of 4, where the parent population had a standard deviation of 2, would mean that, let me try to get this out simply, that the standard error of the resulting sampling distribution would be 1. I want to just make a point about Rule 2. Note, our formula for the standard error is exactly correct, theoretically, for an infinite population. Okay? It's approximately correct for any reasonably sized population. I like to talk about 8 million New Yorkers. For a population that size, it's going to function correctly as regards the sampling distribution. But we have to remember, sometimes it's important to remember, that for finite populations, meaning populations that aren't infinite, the sample size has to be less than or equal to 10% of the population size, or this isn't really going to work. If your sample size is larger than about 10% of your population size, then what you're going to find is that the errors and imprecisions stack up so much that this formula is no longer exact. It may not be precise enough for you to be able to do a lot of useful work with it. But that's, for a lot of work that people do in the medical sciences and so on, that's not really an important rule. Generally, your sample sizes, or rather your population sizes, will be large enough to support the work that you're doing. Here's our third rule. If the parent population, that's really a term that I like to use quite a bit. If the parent population is normal, and I'm using the term normal to indicate that it's normally distributed, it's got a unimodal shape, it is symmetrical, tapers to the edges in the normal fashion, in the exact shape that would allow the empirical rule or the normal distribution table to work for it. If the parent population is normal in that way, then the sampling distribution, that means sampling distribution of x bar, is also normal. So as long as the parent population is normal, the sampling distribution is automatically normal too. It's going to be normally distributed. It has the same mean. It might have a different standard deviation, but it's normally distributed. Okay, this fourth rule is really interesting. Rule number 4. Rule number 4 says if n, your sample size, is sufficiently large, then you have normality, meaning a normally distributed, normally shaped sampling distribution regardless. What does that mean? Okay, let's take a look. Remember, if your population distribution is normally distributed, your sampling distribution is going to be normally distributed too. But let's just say that you have a population that has a completely weird and unnormal distribution shape. It's not symmetrical, it has bumps. Maybe it would have a dropout somewhere where there's no scores. Anything as weird as you can imagine. If your sample size is sufficiently large, then you're going to actually end up getting a normally shaped sampling distribution. Now, as it happens, for that n to be large enough, it doesn't have to be that huge. As long as n is equal to or greater than 30, you're going to have a normally shaped sampling distribution. Remember, this is the population. We're taking samples from it. We're taking the means of all the samples, and we're taking those means and graphing them on a curve. If we take all the possible samples from this funny population, and we take their means and graph them, as long as our sample size is 30 or greater, we're going to have normality regardless. This is part of the power of this tool. It's kind of mathematical alchemy. We're going to make gold out of something, out of lead, out of something much less valuable. We're going to have a normal distribution, which is such a powerful tool. We're hoping to be able to have a normal distribution for a lot of the statistical procedures that we do. And this allows us to take data and have a normal distribution come out of it, even if it doesn't start out as a normal distribution, as long as our sample size is 30 or greater. Remember, we're taking every possible sample. How does this work? Let's think of it this way. We have a distribution, and I just drew something as weird and wonky as I could think of. Here's a distribution that has gaps and asymmetries and just a funny shape regardless. Please remember that we have an enormous number of samples possible from a population. If you'll remember, when we had a population of 50 and we were taking samples of 2, from a population of 50, the number of samples we had was 1,225. That's a lot. And as your sample size goes up and your population size goes up, you have this rapidly increasing number of samples possible, and they all have means. Not only that, but as you increase the amount of samples that you're taking, they increase most rapidly near the mean of your distribution. Let's put that right there. So you have a rapidly multiplying number of samples. They're multiplying very quickly near the center, and they actually are fewer and fewer at the edges. I'm explaining how it is that we get a normal distribution, and I'm going to get there. Let's use a tool to illustrate how this works. Let's go back to our population of 50. So we have a population of 50, and those 50 scores are arranged in kind of a peculiarly organized way, right? We're measuring something. If you want to imagine something from science or medicine, go ahead and do that. Let's just imagine it. So we have 50 scores, and they have to be super organized, and one score has a value of 1, and the second score has a value of 2, and the second score has a value of 3, and so on. So here's our distribution of scores. I left out the middle because I don't have enough room. We have 50 scores in the population. Now we're going to start doing a sampling distribution and taking samples of size 2. What happens? Well, the first thing I notice is that the lowest score and the highest score will change. Now we're going to take, this was our regular distribution. We can think of that as being a sample size of 1 if you want to think about it. It's a little abstract, but not too hard to get. Now we're going to take samples of size 2, and we're going to take a look at the scores we get when our sample size is 2. Think carefully. What is going to be our smallest score? Well, the only way for us to get a smallest mean is to take the one sample that happens to have our two lowest scores. So our lowest score will now be this mean, the sample that includes these two scores. And that's going to be 1.5. Now, let's notice our new lowest score is higher than the previous lowest score. The same thing happens at the other end. Our highest score is going to come from the one sample that incorporates our two highest scores. And the idea that I'm showing you will hold true, these concepts will hold true for any sample size. So our new highest score is no longer 50 like it was when we were talking about individual scores. Rather, our new highest score is a little bit lower, isn't it? So don't let that get past you. The edges of our distribution are shrinking in like your t-shirt in the dryer. It's getting smaller. Instead of going from 1 to 50, now we go from 1.5 to 49.5. Something else happens. Not only do our max and min change when we have a sample size of 2, the minimum goes from 1 to 1.5, the maximum goes from 50 down to 49.5. Not only does that happen, but the rapid multiplication of the number of elements. Remember, we have 1,225 samples of size 2. That rapid multiplication happens most right in the center. We have two center scores. Let's take 25 and 26. That's a potential sample of 2. Remember, we're taking every possible one. So if I take the mean of that sample, I'm going to get 25.5. But wait, there's more than one way to get 25.5. There's 24 and 27. There's 23 and 28. There's 22 and 29, and so on. In fact, we can keep going and getting means of 25.5 until we get back to the very first score and the very last score from our parent population. And we're going to get 25.5 as the mean. So we have two things occurring simultaneously that you want to visualize. The boundaries shrink in. As our sample size goes up from 1 to 2, for example, in this case, the min gets higher, the max gets lower, the boundaries are squeezing in, and there's a rapid multiplication of the number of numbers that we're working with. Now we're talking about sample means, and that rapid multiplication occurs really predominantly in the center because there are so many different combinations that allow us to get middle-ish scores. Remember, there was only one way to get our new minimum, the two minimum scores. There was only one way to get our maximum, the two highest scores. But there's a bunch of different ways to get scores in the middle, and that's where the multiplication generally occurs. So the effect of this is that if we have a funny-looking population curve, I'm drawing it differently every time, then as our sample size goes from 1, that's how we might think of individual scores, sample sizes of 1. As it goes from sample sizes of 1 to sample sizes of 2, our boundaries suck in, the number of scores increase. They increase around the middle, even if our parent population isn't predominantly weighted towards the middle. And they pile up in the center. It's almost like you could imagine a bit of computer animation where the thing seems to sort of grow and melt and squeeze in the center until finally, when we get a sample that is large enough, and we say sufficiently large when our sample size is 30, that what happens is that they pile up so much in the middle and shrink in so much at the edges that it morphs into a normal distribution. By the time n is 30, and I haven't really drawn this to scale because I would run out of board space, it would really squeeze into the center. and it would really poke out of your frame. You wouldn't see the top anymore, but it would be normally distributed. So here's the importance of that fourth rule. Real important, burn it into your memory, that when your sample size is sufficiently large, you can force your numbers to become normally distributed. This is an effect that can't be stopped. If you're sampling every possible sample of some given size out of the population, and your sample size is 30 or greater, it doesn't matter what the population started out looking like. You're going to have a sampling distribution that is normal. That fourth rule, which I've just explained to you in kind of intuitive terms, is also really important in statistics and statistical theory. It's golden. So it has its own name too. Go ahead and look this up. You Google it if you need to or something. Generally rigorous definitions of it. And I've been correct in the way I described it to you, but I'm not using a lot of jargon on purpose. If you look it up, you may find something that appears at first to be impenetrable. But it means basically what I've just told you. It's called the central limit theorem. And it's super important. So let's play around with this a little bit. Let's imagine that we have that population with a mu of 20 and a sigma, a standard deviation of 2, and we're going to take samples of size 4. Now we're talking about samples of size 4. Let's go ahead and describe this sampling distribution, this distribution of sample means. And to describe a sampling distribution is a phrase that's commonly understood to mean talk about three things. Talk about what mu sub x bar is. Talk about what sigma sub x bar is, the standard error, and address the topic of normality. So let's do that. What would mu sub x bar be? Well, this is probably the easiest formula you're ever going to use in statistics. Mu sub x bar, this is rule 1, mu sub x bar is equal to mu, so we know what mu sub x bar is, it's 20. The standard error, sigma sub x bar, is sigma from the population divided by the square root of your sample size. I'm proposing a sample size of 4. Again, we did that earlier. That's going to be pretty easy. So our standard error is 1. But just finishing the package, describe the sampling distribution. Is this going to be normal? Answer, we don't really know. Okay. If this population is normally distributed, then this sampling distribution will be normally distributed also. But if it isn't, then the sampling distribution would not very likely be normally distributed. So the way that we're going to answer this part, the way we're going to talk about normality in the case of this population and this sample size, is we're going to say it is not normal, or rather, we cannot guarantee it to be normal if we don't have any knowledge of the population distribution shape. If you know that the population is normally distributed, then we can turn around and say, okay, yes, it would be. But until we have that knowledge, we have to move forward in describing the sampling distribution by saying, no, it can't be guaranteed to be normal. Let's do another one. Let's imagine a population with a mean of, let's see, let's make it 30 this time, and a standard deviation of 15. Now take a look at that. That already raises red flags for me, because depending on what it is that we're talking about, if we're talking about values that cannot take negative numbers, then already I know that the thing isn't normally distributed, right? Can you see why? That would mean that the lowest possible score, remember, if it can't be negative, the lowest possible score, which would be 1 or possibly some small non-zero decimal, would only be 2 standard deviations away from the mean. And even in finite populations where they don't follow the theoretical rule that normal distributions are asymptotic and go to infinity, you'd still need the thing to be able to reach 3.5 or so standard deviations in both directions away from the mean for you to be able to consider it, okay, it's close enough to normal for me to consider it normal. That's not the case here. That's only 2 standard deviations away, going from the mean down to 0, because the standard deviation is 15. So right off the bat, I'm thinking, okay, if this thing does not permit negative numbers, it's not normal. But from this population, we're going to take a sample size of 36. So that's now above 30, so I can now rest easy. The sampling distribution will be normal. It'll be as if it's forced to be normal by my sample size being greater than 30. What's mu sub x bar? 30. I'm describing the sampling distribution. What is the standard error? Well, following the formula, it's sigma divided by the square root of my sample size. Do it on your own. I think it's about 2.5. Is it normal? For sure. It sure is normal. Our sample size is greater than 30. So we have normality. And by the way, we now have plenty of room from our mean to 0 to incorporate all the standard deviations necessary for it to be a symmetrical normal distribution. Our new standard deviation for our sampling distribution is 2.5. So if I need to go 4 standard errors to the left of the mean, okay, let me draw a distribution right here. I'm right at the bottom of the screen, but I'll squeeze it in. Here's our sampling distribution. This is not the parent population. We have a mean of 30 and a standard error of 2.5. So I can go back and forth 4 standard errors, and I'll still only reach downward to 20 and up to 40. In other words, I got plenty of breathing room. I'm not going to bump into that 0 that in this theoretical situation that I'm imagining and talking to you about, I can't go to. Maybe we're measuring something that can't take on negative values. I think you probably have an idea of what I'm talking about there. If you don't, leave a comment and I'm going to clarify as well as I can, maybe even add in a follow-up video. Let's talk about the Z-score formula again and just relate it to this new construction that we're imagining, the sampling distribution, and for this video specifically, the sampling distribution of sample means. Normally, your Z-score formula for a population will be x, the number that you're examining, you're solving for its Z-score, x minus mu, the mean, divided by the standard deviation sigma. So that's normal. You're probably somewhat familiar with that by now. The Z-score formula with sampling distributions of sample means, is actually really the same thing. I want you to think of it as being the same thing. It looks a little bit different, slightly, but it's really the same thing. We are solving for some value of interest. Now, with sampling distributions of sample means, we're talking about the means of samples, not individual scores. So I'm going to write x bar there because now that refers to the mean of a sample. The mean of the overall curve is not mu, but rather mu sub x bar. This shouldn't bother you. They're always the same number anyway. But we're filling in the Z formula with symbols that are appropriate for this new object that we're working with right now. We're going to divide by the standard deviation, which is appropriate for the moment. That's going to be sigma sub x bar, not just sigma. That's the Z-score formula that we're going to be using when we do the sampling distribution of sample means. We can also write it this way. X bar minus mu sub x bar divided by sigma divided by the square root of n, because after all, that's the same thing as that thing. And that's the formula for it. So you're going to see it both of these ways as it relates to the distribution of sample means. Okay, so that's the first of this series of 3. In the third part, remember, we're going to be doing problems and I'm going to solve them for you during the video, part 3, about the sampling distribution of sample means, as well as about what we're going to talk about in the second video in this series, the next video in this series. But let me just give you something to tide you over, okay? Something to think about. Let's imagine we have that distribution with a mean of 30 and, because I like this example, a standard deviation of 15. That's the parent population. And we're still talking about samples of size 36. I want you to tell me something. Out of all the many samples taken, which sample mean would it be such that it would have a z-score of 2.8? I'm going to answer that at the beginning of part 2.